Right, I want to introduce you guys to expectation operators. So you'll see this notation. And I think the best way to actually start the introduction of these is to start with an example, an idea on this. So suppose we have a raffle, and the raffle has 10 different tickets. Two of the tickets are valued at 1. 5 of the tickets are valued at 2. And then 3 of the tickets are valued at 5. And so, what an expectation operator is telling us to do essentially is it's saying, okay, we want, actually, we want to take the sum of AI times the probability that X equals AI. And what do I mean by AI? Because oftentimes you'll see this in textbooks and probably your lecture, and they'll give you this formula, xi probability x equals xi. This is really sloppy notation, in my opinion. This is very, very sloppy. The issue with this is it conflates what we're trying to capture here. So when we say, if we start with what I'm saying, AI instead of xi is, we take probability of x, that x equals AI. AI is the value of a category. So it's a shared value. So in this case, we'd have 3 AIs. We have AI, let's call it 1. So A1, and that shared value equals 1. We have A2, their shared value equals 2. And then we have A3, which is just a third subset of this larger set, and their shared value equals 5. Why I don't like the XI notation is because it gives this impression that, oh, well, that means X1 or X2. And then I'd say, okay, which one? Because we would say, okay, if we just indices, so we did indices like this. This is person 1, 2, 3, or ticket 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so if we're taking only the probability of observation 1, well, then that's just 1/10. And so it's not telling us anything because the probability of each individual observation is 1 over n. Whereas the expectation operator, the general formula is saying no, if we have shared values, we have a weighted probability. And so we'll do that calculation instead. It's not necessarily wrong to do it. We'll arrive at basically the same conclusion, because the goal of either of these is essentially we're asking what is the average of the set. It's just I I generally would recommend sticking more with the probability concept and notations early on, because then you'll get less confused, especially when we do proofs and that sort of thing, related to, say, like, why we don't have a 1 over n. It's because it's already incorporated in each of these probability values that we're basically saying, oh yes, for each probability that's out of the n observations. So for this, if we were to do this, we would say, okay, A1 equals 1. So that's the value here. So that's telling us take the actual value itself, 1, and then multiply it by the probability of that value out of this set. Well, we have 1 2 times out of 10, so the probability of that is 0.2. You can see where this saves time from, say, taking an average this way, where we have to account for every single term. That takes more time sometimes. And so if we can kind of just lump numbers together and say, yeah, well, we have 5 2s. So I've got the value of 2 multiplied by then, I'm sorry, 0.5. Yes. Lost my train of thought there for a second. And then A3, same thing. Its value is 5 for its set multiplied, and then it's 0.3 because we have 3 observations out of 10. And then if we calculate these, this one's going to equal 0.2, this one's going to equal 1, this one's going to equal 1.5, and then we want to sum them. That's what sigma is telling us to do here. And then that's going to equal 2.7. So our expectation operator equals 2.7. And one way I want you to think about this, so a couple of ways. Most of the time when we talk about these, it's considering a population, not a sample. So that's why we're saying, okay, we're dividing by n. You'll start thinking about that when we relate these to variance and that sort of thing, that, oh, in fact, we're not controlling for a degree of freedom. That's why. Secondarily, as far as like our draws are concerned, so the idea is, obviously you cannot draw a ticket that is valued at 2.7. This is just, the idea behind these is, suppose I kept drawing tickets an infinite number of times. So I can only draw one ticket at a time, and then that gives me a particular value from this whole set. And so as I draw an infinite number of times, my probability of drawing a 1, I will do that about 20% of the time. As I draw a 2, I'm going to do that I'm going to do that 50% of the time. And then as I draw 5s, I'm going to do that 30% of the time. And so there's this idea of it's sort of this perfect averaging where it's saying, yes, redo the draw an infinite number of times, sum the values of those draws, and then divide by n as n approaches infinity, essentially. And you will arrive at this same central value of 2.7. So that's the big takeaway. That's the punchline on this. After this, we'll start getting into central moments of our using expectations operators, and so you'll see how those kind of play out. But yeah, really first, just the basic expectation operator. You could think of it as the mean, but you want to make sure that you're thinking of it in terms of probability, because these actually already have the division of n built into them. So it's not something that needs to be repeated. So with that, I will see you guys next time, and thanks for watching.